A mechanical wave is, by definition, a moving disturbance. It occurs when particles in a medium oscillate, propagating energy from one point in space to another. Drop a pebble in a still pond, and you see this traveling wave in action. The water itself mostly moves up and down, but the geometric pattern of the energy ripples steadily outward. But if you take two identical traveling waves and send them crashing into each other from opposite directions, their collision creates an entirely different phenomenon, a standing wave. Look at this comparison. On the left, the traveling wave's crests continuously move laterally across the screen. On the right, the standing wave's crests and troughs pulse vertically, oscillating perfectly in place. In this state, the medium halts the physical transfer of the pattern. The energy is contained, locked into position by the precise interference of its own reflection. To understand how a wave stops traveling, we rely on the principle of superposition. This rule dictates that when two wave disturbances overlap in the same medium, the net displacement is exactly the sum of the two individual waves. This animation shows exactly how the math works. We take a sine wave moving right, add it to an identical sine wave moving left, and they merge into a new equation. The resulting displacement is 2 times the amplitude times the sine of kx, all multiplied by the cosine of omega t. Notice that bracketed section. In a traveling wave, amplitude is a constant number. Here, the amplitude is a function of position, x. Your vertical swing depends entirely on where you sit on the horizontal axis. In this standing wave, specific locations marked in red are points where the sine function equals 0. We call them nodes. The medium here never moves. Sitting exactly between them are antinodes. These green markers indicate the largest possible vertical oscillation. This mathematical structure reveals a standing wave is a highly stable interference pattern. The energy isn't flowing laterally, it is permanently localized between the nodes. The scientific analysis of this kind of motion dates back to the 17th century. Physicists mapped the behavior of elastic media by studying the oscillations of coiled springs and pendulums. What those early models showed is that physical constraints dictate the motion. If you take a string and rigidly clamp it at both ends, you introduce a boundary condition. Those tied down ends have 0 displacement, meaning they must be nodes. This diagram illustrates the result. Because the boundaries are fixed, the string physically rejects arbitrary frequencies. It can only host wavelengths that fit perfectly into the space as integer multiples of half wavelengths. This restriction yields a specific set of natural frequencies for the string, which physicists call its normal modes. This diagram shows the lowest possible natural frequency, known as the fundamental mode, or first harmonic. The entire string vibrates as a single large loop, with nodes only at the clamped ends. As you excite the higher harmonics, by plucking a sitar, for instance, the string divides itself into multiple vibrating segments. The second harmonic introduces a node in the exact middle, creating 2 loops. These stacked normal modes are what give the instrument its complex tone. This same logic applies to 2-dimensional systems. On a tabla, the entire rigid circumference of the drumhead acts as the boundary condition, forcing the circular membrane to vibrate in specific geometric modes. A system cannot oscillate freely when it is anchored. By placing physical boundaries on a medium, we force its energy to organize into standing waves. The restriction of motion is exactly what creates the structure of music.